Section 1. Introduction. The simplest way to calculate the least common multiple of two positive integers is to write out all their integer multiples and look for the first one that's greater than 0 and common to both. Here's an example. I've drawn out all the integer multiples of 4. I'll call the set of these numbers 4 times z. And I've drawn out all the integer multiples of 6 to get 6 times z. And let's look at where they overlap. You can see they overlap at 0. The next time they both overlap is at 12, then at 24, 36, and so on, and all the negatives of those numbers as well. In other words, 4z intersect 6z equals 12z. This is the same thing as saying the least common multiple of 4 and 6 is 12. Also notice the fact that 12z is contained in 4z, that is, all multiples of 12 are also multiples of 4, says that 4 divides 12. Sets like this 4z are a surprisingly powerful tool. Kummer called them ideal numbers, and nowadays they're called ideals. So, section 2. Ideals. If you know the algebra behind these already, I'll try not to bore you in this section. Ideals are defined as follows. Let R be a ring. A non-empty subset I is called an ideal if whenever two elements are in I, their sum is in I, and whenever an element is in I, you can multiply it by anything else in the ring R. So for example, 4z is an ideal of z, because if you add any two multiples of 4, you get another multiple of 4. And if you take a multiple of 4 and you multiply it by any integer, the result is still a multiple of 4. Here's another example. Let's try all the multiples of 2 plus I inside z adjoin I. Okay, so 2 plus I times 0, times 1, times 2, and so on, times minus 1, times minus 2. We also have to multiply it by I, because I is an element of this ring, and then 2i and 3i and their negatives, and now we have to multiply it by 1 plus I, or in other words, take this point here and this point here and add them, okay, and so on. The set we get at the end is the ideal of z adjoin I generated by the element 2 plus I. I'm going to write that as 2 plus I times z adjoin I, or sometimes I'll just write 2 plus I in brackets if the ring is clear from the context. Now if you wanted to, you could also draw out 2 minus I, and you could see that where they overlap, where they intersect, is 5, as you might expect from the previous video. This already has one interesting feature. Ideals can't tell the difference between units. For example, 2z and minus 2z look the same. All the integer multiples of 2 and all the integer multiples of minus 2 are the same thing. And that's because 2 and minus 2 are associate in z. One of them is the other times a unit, minus 1. Similarly, 4zi and 4izi are the same thing, because 4 and 4i generate the same ideal, because I is a unit. So ideals don't see units. But we haven't just done this to find a new way of writing numbers and ignoring the units. The real reason we've done this is that not all ideals come from a single number. Not all ideals are generated by a single element. We'll come back to that. Section 3. Ideal arithmetic. We've already seen that the intersection of two ideals corresponds to the least common multiple. And there are other arithmetic operations on ideals as well. For example, we can define the product of two ideals, I times j. That's just the ideal generated by all the elements, little I times little j, where I is in I and j is in j. And this corresponds to the usual product of numbers. A multiple of 4 times a multiple of 6 is a multiple of 24. But the really important operation, for our purposes, is rather confusingly called the sum of two ideals. This has nothing to do with the usual sum, or rather it does, but the connection's not immediately obvious. The sum of two ideals is defined as follows. You take all the elements little I in I and little j in j, and you add them and you see what ideal they generate. In other words, you take all the points in I, all the points in j, and you take their union, and then you find the smallest ideal generated by adding together all the points you already have. Right, so for example, 4z plus 6z can be calculated by taking the union of these two sets, all the multiples of 4 and all the multiples of 6, and then adding in whatever's necessary to make sure the result is an ideal. So for example, this set contains -6 here, and it contains 8 here, so it had better also contain their sum, which is 2. Remember Bezout's lemma? The ideal sum corresponds to the greatest common divisor of two numbers. So here's the real point. Ideal sums are greatest common divisors. Remember that I said not all ideals are generated by a single element. The ones that are basically just numbers, except we're ignoring units. They're called principal ideals, and they behave more or less like numbers. But there are also non-principal ideals that can arise when you take sums of principal ideals. These don't correspond to any numbers we have in the ring. They're like greatest common divisors that don't exist, but perhaps should. Here's an example. We've discussed this one before. Remember that in Z adjoin root minus 5, the number 6 factorizes as 2 times 3, and also as 1 plus root minus 5 times 1 minus root minus 5. These factorizations are both minimal, all 4 of these elements are irreducible, but it feels like there should be some underlying, even smaller factorization, underpinning them both and making some kind of uniqueness of factorization possible. In the ring Z adjoin root minus 5, these elements don't share any factors. But if we convert this to a product of principal ideals, let me just put brackets around them, suddenly we do have extra factors available to us. Here's the ideal generated by 2, and here's the ideal generated by 1 plus root minus 5. We wanted them to share a prime factor. Okay, well here's their ideal sum. Let's call it P1 for prime. And I'm going to write it like this. It's going to be the prime generated by 2 and 1 plus root minus 5. We can do the other pairs as well. Here's P2, P3, and P4. Notice, by the way, that P1 and P2 are the same. We'll come back to that. It's a good exercise to check that when you multiply P1 and P2, you get the ideal 2. When you multiply P1 and P3, you get the ideal 1 plus root minus 5, and so on, like I promised in my previous video. Section 4. Recovering unique factorization. Okay, I need to say this at some point. Our rings of interest, like Z, Z adjoin I, Z adjoin omega, Z adjoin root minus 5, are called Dedekind domains. One way of looking at this theory of ideals is to see it as adding in all the missing greatest common divisors necessary for factorization to be unique. In fact, due to the way Dedekind domains are defined, we have perfect analogues of greatest common divisors, primes, Euclid's lemma, and unique factorization, but only if we work with ideals, not elements. Now, if all ideals in your ring happen to be principal, generated by one element, then we are basically just working with elements without bothering to write the units. So we get a unique factorization of elements 2 up to some units. Secretly, that's what we were doing when we were working inside Zi and Z omega. In a Dedekind domain, having unique factorization of elements and having all your ideals be principal are the same thing. Okay, so how does this help? Well, if our ring isn't a unique factorization domain, we can still perform calculations on the level of ideals as if it was. Here's a table of how the prime ideals of Z factorize into prime ideals of Z adjoin root minus 5. It's a slightly more complicated story than before. 2 factorizes as we saw before, 2, 1 plus root minus 5 times 2, 1 minus root minus 5. But actually, we saw earlier in our diagrams, these are the same ideal. We've written them differently, but they turn out to be the same thing. So 2 is the square of some prime, P2. It ramifies. Okay, 3 splits as we saw before. 5 ramifies. It's just the square of root minus 5. 7 splits. 11, 13, 17, and 19 remain inert. 23 and 29 split. 31 remains inert. The secret underlying pattern is only 2 and 5 ramify, primes that are 11, 13, 17 or 19 mod 20 stay inert, and primes that are 1, 3, 7 or 9 mod 20 split. By the way, the units in z-adjoin root minus 5 are plus or minus 1. And you can check that for yourself as well. Let me remind you that the norm function on this ring sends a plus b root minus 5 to a squared plus 5b squared. In particular, like in zi, this never takes negative values. Okay, so it looks like we have a perfect understanding of multiplication in z-adjoin root minus 5. But there is a snag. Many of these ideals aren't principal, and here's why that matters. Section 5, an example. Show that there are no integer solutions to the equation y cubed equals x squared plus 5. Here's a sketch solution. We'll do sort of as we did before. We'll factorize the right-hand side in z-adjoin root minus 5. We get y cubed is x plus root minus 5 times x minus root minus 5. Now, if z-adjoin root minus 5 was a unique factorization domain, we could apply the fundamental lemma from a couple of videos ago. Once we've checked that x plus root minus 5 and x minus root minus 5 have greatest common divisor 1, which they do, we can conclude that x plus root minus 5 is itself the cube of some element, say d plus e root minus 5, where d and e are integers. Okay, a quick bit of algebra leads us to conclude that e squared must be 4/3 or 2, both of which are obviously not possible if e is an integer. Now for this to work, we need z-adjoin root minus 5 to be a unique factorization domain. We know it's not. So let's try something else. Let's just make all these numbers into principal ideals. Okay, I'm just going to put brackets around everything. Now everything is an ideal. Now, ideals do have unique factorization, and so they have their own version of the fundamental lemma. Once we've checked that the ideals, x plus root minus 5 and x minus root minus 5, have greatest common divisor 1, which they do, we can conclude that x plus root minus 5 is the cube of some ideal. Okay, but now what? If this ideal is principal, we're back to working in the world of numbers. But what if it isn't? And how can we tell? In other words, we started out with a question about numbers, and if we'd been working in a unique factorization domain, we could have just got a solution in terms of numbers straight away. But we weren't. So, we turned it into a question about ideals, where the calculation was easier, and we found a solution there. But now we want to translate this back into numbers. How can we do that? When can we do that? In this case, we have that some ideal a cubed is x plus root minus 5. Now that's principal. X plus root minus 5 is a single element. So a cubed is principal. So what happens if I take a principal ideal in this ring and I sort of cube root it? Is it possible that I can take non-principal ideals and multiply them together to get principal ideals? Or do they somehow get even worse? Do I need more and more elements to generate them each time? Can they get messier and messier? We'll discuss this in the next video.